So yesterday we learned sine is equal to the wall when the ladder is length 1. Cosine is equal to the ground when the ladder is length 1. Why else do we like the ladder length 1? Right. If the ladder is length 1, then the height of the wall, or that length, is equal to the percentage. And that is so important you don't realize it, and you won't for a little bit. But yesterday we looked at the example, the sine of 37 equals 0.6. What does 0.6 mean? 60%. The wall is 60% as long as the ladder, unless the ladder is length 1. Right, so this is simultaneously 60% and 0.6 units, and we don't care what the units are, so we're just going to say 0.6 ladders. So that wall height is simultaneously a percentage and a length. Remember that, because I'm going to come back to it later in this lesson. What about tangent? Tangent is wall over ground. Does it matter what the ladder is? No. But you do notice that wall over ground is the same as sine over cosine. And actually, the tangent is always sine over cosine, no matter what the length of the ladder is. For example, we did the tangent of 35 degrees, and I did the sine of 35, not 5, 35. And then I divided it by the cosine of 35, I'm going to get that same 70%. And that's always true. We also learned yesterday, if you have a sine button on your calculator, you don't need a cosine button. How do sine and cosine relate? They're complements. The sine of 20 is the cosine of 70. The sine of 10 is the cosine of 80. So sine of theta equals the cosine of 90 minus theta. That's always true also. Okay. So if we want to extend theta to angles bigger than 90, that will destroy the right triangle. But first you have to know how to make angles bigger than 90. What's the biggest angle you can think of? 360. What's the smallest angle you can think of? 0. Anybody in here a skateboarder or snowboarder? Connor? Deer Hill Clicker? As a snowboarder, are you limited to a 360-degree angle? I am. I mean, a 10-degree turn would put me on my face, but other people, are you limited by 360? No. How come? You just keep spinning, right? So, define for me a degree. It's 1/360th, and we're missing a word. 1/360th the blank of a circle. What action does a degree do? Rotation. Exactly. It's 1/360th the rotation of a circle. Are rotations limited to 360? No. Are they limited to 0? You can be negative. Is there a difference between a 360 and a reverse 360? Right. They're going to end up facing the same direction, but the actual process is different. Okay. Take a look at the first page of your worksheet. So we have a dial here, and notice the names of the quadrants: QI, QII, quadrant 3, quadrant 4. Have you ever wondered why we do them in that order? Starts on the top right and goes counterclockwise. Well, this is kind of the most important quadrant, right? Well, this quadrant 1 makes sense, right? This is the only quadrant where the x and y is positive. We spend most of our time in quadrant 1. But why does it go counterclockwise? Well, I'm going to teach you. Suppose we have a dial, and the dial is anchored at the origin, and then the dial extends along the positive x-axis. So right here. When we're measuring angles in the Cartesian plane on the xy graph, this line is called standard position. And this is one of those things in math that never changes. Standard position is always the positive x-axis. And now, when we measure positive angles, we rotate the dial counterclockwise. So any rotation from standard position in this direction is considered positive. And notice that the quadrants are named and numbered according to the order that the dial passes through that particular quadrant. So quadrant 2 is the top left because it's the second quadrant that the dial hits, and then third and fourth. And just as a kind of a side note, there's a big difference between QII and Q2. This means quadrant 2, which is exactly what we're looking at. This means quartile 2, which is a statistical. Anyway, we'll get to that. We'll study quartiles at the end of the year. So don't ever write Q with the number 2. You can go ahead and call it quartile or quadrant 2, but always use the Roman numerals. All right, so you see a bunch of angles here. If you look down, there are a couple questions. When turning the dial counterclockwise, what angle will place the pointer on the positive y-axis? Positive y-axis, 90. And I've built these nifty little measurers. So that's standard position. If I turn this dial, that's 45 degrees right there, 90 degrees. So the positive y-axis is a 90-degree angle. So if I were to say graph a 90-degree angle, you would draw this. And actually, because it's understood that all angles begin in the standard position, we don't even need this line. That represents a 90-degree angle. Well, you have to have the graph. You have to have the graph. And then that's a 90-degree angle. This side is called the terminal side. What does terminal mean? Anyone ever ridden public transportation, buses, trains, streetcars? The bus stop is also called a bus terminal because it's where the bus stops. A train station is also called a train terminal because that's where the train stops. So terminal, so you have two sides to every angle. You have the standard position, and then you have the terminal side. So the terminal side means where the angle stopped. It always begins in standard position. But wherever that line ends is called the terminal side. Okay? So how far do I turn the dial so the terminal side ends at the negative y-axis? So if I turn my little dial over here, 270. What about the negative x-axis? So that would be negative 180. What about all the way around? 360. Okay? Easy stuff, right? In what quadrant would the angle 25 degrees land in? 1. How come? And there are two things we need to look at. 25 is bigger than 0 and less than 90. Everybody agree there? Okay, what about 279? Why 3? 4. Okay, why 4? Bigger than 270, less than 360. Now, do you want to see another way to do that? And this helps with really large angles. If I took 279 and I divided it by 360, what does that number tell me? It's 77% of a circle. Where would 77% of a circle end up? 4. How come? Because 3/4 of the way around is 75%, and all the way around is 100%. So 77% is bigger than 75 and smaller than 1. Okay? What about 89? 1, how come? It's just slightly less than 90, obviously bigger than 0. So if I did 89 divided by 360, what should I expect? Should be really close to 25. Slightly below 25. And it is. All right, 125. Where does 125 land? 2. It's bigger than 90, less than 180. So what would I expect this decimal to be? 30, 40%, somewhere in there. It's got to be less than 50 and bigger than 25. Okay. 370. Where's that going to land? 1. Why? All right, if I draw this picture, we start in standard position, we go all the way around. And 10 more degrees. So the terminal side is going to be right there. If I find the decimal, what would it be? 1.1, 1.2. So 370 divided by 360. You're right. It's a percentage of the circle. So this top one is 24% of a circle, which is less than a fourth. 34% of a circle, which is between 1/4 and 1/2. And 1.02 means 1 full circle and 2% more. Okay? So does this 1 do us any good? Well, it tells us something. It tells us how many times we went around. Do we care? Why not? Now, if you're a snowboarder, does it matter? Yeah. Right, a 360 is not as cool as a 720. And an 18-degree rotation is called a crash, if I understand my snowboarding right. Okay, but in mathematics, we don't care how you get there. The only important thing in these angles is where the terminal side lands. So for all intents and purposes, 10 degrees and 370 are exactly the same thing. And if you don't believe me, try the sine of 10, and you get 17%, or 0.17 ladders, or the sine of 370. It's the same number. Okay, hang on to that. We'll deal with that a lot in the future. What about this 720? So which quadrant? Well, we know it's 2 full rotations. Which quadrant is that in? Between 1 and 4. It's not in either of them. It's between 1 and between 4. So I have a question. What if I give you a really big angle? 815. How are you going to figure out where that lands? Well, and you're right. Let me back up a little bit. So I'm going to take 815 and I'm going to subtract 360. What's wrong with that number? Still too big. So I subtract 360. 95, which means quadrant 2. Okay, is there a faster way to do that? So 815 divided by 360. What is that telling me? 2 full rotations. Do we care? No. Plus 26%. 26% is in quadrant 2. So if I had a humongous number, that's big enough, right? That's a pretty big angle. Divide that by 360. Which quadrant does that land in? 1, because it's equivalent to 9%. 9% of the circle. So this big long list of numbers just tells me how many revolutions we did. No. So if you don't quite understand that, let me draw the picture. So this is 25%, this is 50%, This is 75%, and this is 100%. Well, so if we look here, this 815 divided by 360 is 26%, which is quadrant 2. The other one is 9%. So you drop the whole number and you just look at the percent. Now, if you don't like that, that's okay. But in the next thing we learn, you need to know how to do this because it makes things, you'll think it's easier. I prefer doing it a different way, but you'll like this way better, probably. Okay, so turn the page. So now we're just going to turn the dial the other way. It's hard to see that, but that says negative 111. So if you take the dial in standard position and you twist it clockwise, then you end up with negative angles. Now, it's important to note that the quadrants do not change names. It's still 1, 2, 3, 4 in counterclockwise versions. You just answering those questions. Yeah. So, you might not be, but the rest of us are. So go ahead and answer all the questions on this page. It's the same as the other page, but now we're spinning the other direction. Okay? So I'll give you a minute to work on that. Whatever. All right, turn the page. After turning the dial in both directions, it's obvious that turning the dial 90 degrees is the same as turning the dial negative 270. And these two lines terminate in the same position, so we call the two angles coterminal. They share the same terminal. It's the same bus station. And we don't care what bus you ride to get there. All we care is where you stop. So 90 and negative 270 are exactly the same angle. To show you again, the sine of 90, we know what this is. How high is the wall when the angle is 90 degrees? 1. That should be the same thing as the sine of negative 270. And it is. Okay? Now, this will blow you away. What about the sine of negative 15? Oh, I used the wrong button. Wait a minute. How does that work? All right, we'll talk about that later. I plugged in a sine value and I got a negative number. Can the wall be negative? So I drew an angle such that this value was negative. We'll talk about it later. Well, you've seen it before. They haven't. Okay. So I'm looking at this coterminal angle 116 with negative 244. If I have the angle 116, how do I create a coterminal angle? Let's say that my coterminal angle needed to be negative. Subtract 360. Can I represent that in the picture? So I rotate till I hit 116. That's this portion. And then I reverse directions for an entire circle. And those two angles are coterminal. Yeah, so the angle I was looking at, and if I subtract 360, I get negative 224. What if I want another negative coterminal? Just go around again. What if I wanted a positive coterminal? So I take my original angle, and then I go all the way around again. So let's suppose that I'm looking at a 900-degree angle. First of all, where does a 900-degree angle terminate? Well, let's divide this by 360. 2.5, where's that going to land? It's the same as 180 degrees. It's the negative x-axis because it's 50% of the circle. Okay. So let's find a negative coterminal angle. So I'm going to take 900, I'm going to subtract 360. It's not enough. So I subtract 360 again. Oh, hey, look, there's the 180 we talked about earlier. If I do it again, now I have a negative number. How many negative answers are there to that problem? An infinite number. So any angle has an infinite number of coterminal angles. In fact, it has an infinite number of positives and an infinite number of negatives. Okay? So when you're answering this question on a test, please give me the first answer. Because if you're really cynical, you could give me the answer 3,780. And technically you're right, but I don't want that one. I want the first one you happen to run across. If you put that, I'll have to check to see that it's right, and I might swear. So we don't want that. I might swear. Yes. I might give all of my classes U's. Oh, I need to think of something new. Okay. So go through, fill out the first column, the one on the left, take the given angle and state a positive coterminal. On the column on the right, give a negative coterminal angle. It's really easy. So let me describe for you one of the limitations that we have with degrees. So we talked about a degree. What was a degree? It's just a measure of rotation, 1/360th the rotation of a circle. So if I asked you to walk 6 degrees, how would you do that? You can't, right? Degrees are rotations. So if I were to put my arms out and rotate 45 degrees, that's the rotation. Okay? If my arms were longer, does that change the rotation? No. So, one of the things we want to be able to do is to graph y equals the sine of theta. And this graph is incredibly important. I mean, it's so important you won't even know. Your cell phone uses it all the time. We need to understand how that graph works. Well, we do know some things about it. I made a chart the other day, sine of theta, and we decided what type of numbers go in to the sine. Angles. So we did 0, 15, 30, 45, 60, and so on. What kind of numbers come out? If I plug in an angle, what do I get out? Percent. So this is a theta, and this is a percentage, and I happen to know these, 0, 0.25, 0.5, 0.7, and 0.86. Okay? So I can start a graph. Okay? The trouble is, these are two totally different units. One is a degree, and one is a percentage. And this graph is so important, I need to draw it to scale. I need to understand the scale of the graph. But there's no relationship between these two numbers, Connor. They're totally different. And which one of those represents a length? None of them, right? A degree is not a length, and a percent is not a length. But we fixed that problem yesterday. The percent is a length as long as the hypotenuse is 1. So that's why we fixed this. So instead of percentage, we're going to put this is ladders. Okay? So if your ladder is 16 feet long, I know exactly how far 50% is. It's 8 feet. Okay? So we've worked out the x-axis. So this is going to be theta, and this is going to be percentages, which is actually in terms of a ladder. So say my ladder's that long, that's 1, 0.5, and so on. But how long is a degree? Well, if I say that this is 15, 30, 45, 60, then my graph's going to look like this. What do you notice about those dots? They're slowing down, right? They're rising, but they're slowing down. The difference is a quarter, a fifth, and less than a fifth, 14%. Okay? Well, that could be one graph, but what if I were to cut these values in half? What would that do to the graph? So if I made this 15, it's going to scrunch the graph up, right? And if I lengthen the graph, so if I put 15 over here, what's that going to do? It's going to stretch it out. And the shape of the graph is very important. So, degrees are not good enough. They're great for real-world applications. You're building a tree house, by all means use degrees. They're great for construction, they make sense in your head, but mathematically they create this problem of it's impossible to draw the sine curve to scale using degrees. Good luck. Try it. Try graphing the sine of x and see what happens. Don't bother. It won't work. Nothing, right? And actually, there was probably one little dot there you didn't notice. So, what we need is an angle that is tied to a length. So if I say walk this specific angle, you know what that distance is. If I say spin a specific angle, you know how to do that. Okay? Those angles are called radians. And radians have to be tied to a length. Well, do we have a favorite length? One ladder, one hypotenuse. Okay? Well, this circle that we've been dealing with, okay? Have you noticed anything about the terminal sides? Are they a specific geometric structure? Well, the line itself is a radius of the circle, right? And in quadrant 1, that radius creates a right triangle such that the radius is the ladder. So what we're going to do tomorrow is we're going to link all of these angles to a length. And that length we're going to link it to is one ladder. So no matter what your hypotenuse is, 87 feet, we scrap the 87 feet, we call it one ladder, and then we link that one ladder to the size of a particular angle. So if I said spin 1 radian, all you have to do is turn the correct number of degrees. If I said walk 1 radian, all you need to know is how long is the ladder, and you walk the distance of the ladder. Okay? So stay tuned for tomorrow. We're going to create radians. And the trouble with radians is they're a pain in the butt to work with because visually they don't make much sense. But mathematically they're needed.